Bismillahirrahmanirrahim. Good evening. Today we will talk about the field effect transistor, and we will try to know all of his kinds, what the difference between the field effect transistor and bipolar junction transistor, what's the big story behind all of these three terminals. Now we have three devices take the same form, we can say, the Schottky diode, bipolar junction transistor, field effect transistor. Why all of these have three legs? Why this field effect transistor is very important to us. Let's know all of these important information about this app. Field effect transistor are probably the simplest form of transistor, widely used in both two fields. The first one is analog, the second one is digital applications. They are characterized by a few great qualities: very high resistance, small physical size. They can be used to form circuits with low power consumption. And because all of that, they are widely used in very large scale integration. Now we will be talking about the field effect transistor by use general ideas. After these slides, we will go deeply, we will go on to the another important information, another deeper information related with this topic. Field effect transistor, it's an electric field is established by the charge present, which controls the conduction path of the output circuit without need for direct contact between the controlling and the controlled quantities. Now let's know what are the major difference between the bipolar junction transistor and field effect transistor, because like I said before, both of them has the same out shape. Here, some similarity between, like I said before, bipolar junction transistor about the shape. All of these has three terminals, but all of these terminals are different at B junction transistor and field effect transistor, and we will know all of this information, what the difference between all of them. But at first, let's take that simply. Here, field effect transistor is a voltage control device, but bipolar junction transistor, it's a current control device. Field effect transistor is unipolar device. That's mean either electron or hole. What does mean? That lets me use more easier words. Let me say what that mean unipolar device. That mean device can deal with just one kind of carrier charge. Holes or electrons can dealing with all of them at the same time. This reverse situation with the BJT, bipolar junction transistor, because it can deal with all of these two carrier charge at the same time. Field effect transistor have a high resistance, not like the higher resistance than bipolar junction transistor, more temperature stability, usually smaller than, and it's important to us because we can use it widely in the integration circuits, making them particularly useful in integrated circuit IC chips. Actually, we must know that IC chips, integrated circuits, is very important in nowadays because we use it every day in every car, every laptop, any touch screen. Field effect transistor is a suitable control device. And now all of these two images illustrate to us the different shape. If I take outlook to this shape, all of these has three terminals, but heats is different. And I will explain all this important information at the next slide: the drain, gate, source, here the base, the emitter, the collector, and here by taking another picture, but to inside to these two boxes. This bigger image illustrate to us all these terminals and the book from outside. From inside will be like that. And I will talk about the field effect transistor kinds, the MOSFET and junction field effect are the next slides. Here, the difference between the bipolar junction transistor, that's right, has the same shape, has same number of terminals, but all of these are different. Here, emitter, collector, base, but here, drain, source, gate. Three types of field effect transistor. The first one, and we will talk about it at first, junction field effect transistor. And MOSFET, that's mean material, oxide, semiconductor, field effect transistor. And has two types, and we can say isolated semiconductor field effect transistor. The both of them has the same meaning. And isolated semiconductor field effect transistor has two types, the depletion type and enhancement type. The last kind is metal semiconductor field effect transistor. Now let's talk about the junction field effect, or we can say or write like that, but it's easier. Here, the isolated gate of the material oxide semiconductor is replaced with a reversed biased PN junction. That means we will dealing with reversed bias. The terminals will be reversed. Since the gate junction is always reversed biased, what that mean? That means no current flows into the gate, and it acts like isolated. Sure, because we don't have any current can't flows into the gate. That mean will be like isolated. We talk about the gates of the material oxide semiconductor. But the basic operation, all of these forms as the same. We have three terminals, junction field effect, and three terminals at the most material oxide semiconductor, has the same names. The first one, drain, will be from up. Source will be at the down. The gate will be from the left side. Here, we can start from here, drain, gate, source. Here, the minority, the majority, and the depletion region will be around the minority region. Let's take a look to inside this box. Here, from the gate, the arrow will come from the gate, go inside this circle, the drain, the source. The drain and the source will connect it by use this line, this wire, this piece of metal, I don't know. And here, this image illustrates to us from the both sides, because we know we have two sides of minority. Here, the minority holds around that the depletion region, holds around that the depletion region. All of these depletion region, minority, sorry, all of these minority, all of these holes connected with the gate by use the same source, the same point, the same wire. And here the drain and the source. All of that is the majority. And because that I know it, I'm dealing with N-type junction field effect transistor, because here at first I take a look at the middle, if here N or P, and what is from these two sides, to can decide in which type I'm dealing. Here P channel, this image illustrates to us the minority, the electrons from this side, and the holes at all these huge region. The drain, gate, source. Take a look inside the circuit. The arrow will go out to the gate and the other at the same. All of these minority connected with the gate, drain, source. Let's assume we're dealing with N channel. The major part of the structure is the N-type material, which forms the channel between the impeded layers. Impeded layers, that's mean the holes at these two sides, which forms the channel between impeded layers of P-type material. The top of the N channel is connected through the an ohmic contact at thermal, referred to as drain. That's mean the up point contact by using an ohmic contact with the drain. The same thing with the source. The lower end of the same material is connected through an ohmic contact to terminal referred to as source. The two P-type material are connected together to the gate by using this wire to the gate. Now, in the absence of any applied potentials, what does mean absence? That means we don't have any applied potential. What does that mean? That means we're dealing with the same situation with the no bias conditions, because here, no power source. That means the junction field effect has two PN junctions under no bias conditions. Under no bias conditions, we have the drain source voltage equals 0 and gate source voltage equals 0. To be like that, the minority, the depletion region, and the electrons at in any place here at the middle. The result is that the depletion region at each region will be like the same region of a diode under no bias. Let's translate what that means. That means some similarity between this inside this circle, and inside this depletion region, because here this depletion region will be full with acceptor ions around the P side under the no bias condition. Now let's try to apply some voltage, some positively voltage. Positively voltage, that's mean forward bias, from the drain source voltage. And let's say let's take a look what will happen, and let's plot that by using the current voltage curve. A positively voltage at the drain source voltage is applied across the channel. Let's take 2 volts and more, start from 2 volts, and after that increasing. The gate is connected directly to the source to establish the condition the gate source equals 0. That's mean we will increase the drain source voltage, and at the same time we will make the gate source voltage equal 0. How? By connecting directly the source to the establish, to make it like that. The gate will connect it directly with the source. That will make VGS equal 0, and we will increase the voltage from drain source voltage. What will happen? Let's take a look to these two different images. Here, the middle was full in electrons, and the depletion region, it has a huge similarity with no bias, at no bias condition, with no any power source. But here, after we applied the voltage, the drain source voltage equal 2 volts and more, what will happen? The electrons will be like that to go on to the drain, to this side, and go to the source. And some change will be at the upper of the depletion region, just from the upper, because at bottom points, at the last point from these two sides, will be at the same, will be at the same depletion region at no bias, and the change will be just from the upper points. The gate and the source terminal will be at the same potential. The gate and the source, because we connected it by using a wire to connect the gate directly to the source and make the gate source voltage equal 0. The depletion region in the low end of the region, P material similar to the distribution of the no bias condition. The electrons are drawn to the drain terminal. The electrons are taken to the drain terminal like that. Establishing the conventional current ID from ID to IS, and drain current will equal source current. The voltage, the drain source voltage, is increased from 0 to a few volts. Let's take a look what happened in the current volt curve, IV curve. The current will increase as determined by Ohm's law. Here, this line, we can say this Ohm's law, exponentially increasing. This acts Ohm's law. After that, start to be something like constant. This acts to us the saturation current, the saturation level to us when VGS equals 0. And here, the maximum drain source current will be at gate source voltage equals 0. Let's take a look to these important notes. Here, increasing resistance to narrowing channel. That's mean when increase there is resistance, the channel will be smaller. Here, and channel resistance. Like I said before, the resistance will be constant. As drain source voltage increased and approaches a level as VP. What does mean VP? VP is the pinch of voltage. It will be something like condition to us because we will dealing with it and many times it's in a next curve at voltage equal VP, the current will be near from 0 when we apply a negatively current at the gate source voltage. Let's we will learn all of that at next slides. Let's keep going. Drain source voltage when equal punch off voltage, the depletion region will be widened, will be bigger, causing a noticeable reduction in the channel. Like I said before, the depletion region increase, the channel will be smaller. The width channel will be smaller when the depletion region will be widened, when be bigger, because at this condition, the drain source voltage equal the punch off voltage. Here, the drain source voltage is increased to a level where it appears that the two depletion region will touch, will close the channel. A condition referred to as punch off will result. Punch off will result, where in drain source voltage equal VP, this channel will close. Why? Because the depletion region will touch each other and close the channel to us in the condition when the drain source voltage equal VP. Here, this the pinch off at the pinch off voltage. Let me take a look to a previous slides. I want to prove something. Let me keep going. Just I wanted to say at VP, we have the maximum drain source current. But okay, let's keep going. At drain source voltage increases and approaches a level as a punch off voltage, the depletion region will be widened and casing a noticeable reduction in the channel. That means the width channel will be smaller. I'm sorry, yes, from this side. Yes, will be smaller. Yes, that's right. At the right side. The voltage, drain source voltage is increased from 0 to a few volts. There I will increase as determined by Ohm's law, like I said before, and the resistance is constant. Here, the electrons are drawn to the drain terminal, establishing the conventional current. Here, the result is the gate and the source terminal will be at the same potential. The depletion region in the low end of each P material, similar to the distribution of the no bias condition. I think I did a mistake. Let me close the headphone. That's it. And come back to our lecture. Yes. Now, the drain source maximum current is the maximum drain current for a junction field effect transistor when equal the voltage equal the punch off voltage, and is defined by the condition VGS equals 0 and VDS equal or bigger than punch off voltage, the drain source voltage. Now, when drain source voltage bigger than 0, and let's try to apply negatively voltage, that's mean for reverse bias, to the gate source voltage, what will happen? If we will have the same diagram between the current and voltage, what the difference will be? Let's know all of this important information. Now let's try to apply gate source voltage, start from 0, like the previous curve, and minus 0.5, minus 1, minus 2, until minus 4, and try to plot the diagram between all of these values between the current and voltage. Here, when we put minus 0.5, here it's wrong. Like, I think I take all of these pictures from the different sources, but here it's wrong because must connected it with reverse bias. The negatively terminal must be from here, connected with the minority, with the holes, and the positively terminal must connected with the N terminal. What will be the same thing will be the electrons try to go out from this side, and the current from ID will go to the source current like that. ID direction will be, this arrow will act the ID direction, and the depletion region at the low will be the same with the depletion region at the zero bias or no bias. And we will have change at these upper points. The depletion region will increase to try to touch each other. Here, when we have reverse bias voltage equal -1, the depletion region will grow more, and this will be constant. Drain source voltage equal bigger than 0. The currents start to flow from ID to IS like that, and electrons start to flow from from down to up like that. Here is the controlling voltage of the junction field effect. Here we applied -2. The depletion region, it's bigger. We applied -2.5. The depletion region, it's bigger, and try to touch each other. And the channel here, it's very smaller than the previous situations. Let's plot these two situations when V gate source equal -0.5 volt and equal -2.5. Here, this Ohm's law can act this line. It's exponentially increasing in the current with a few increase in the voltage at -0.5, -0.5, and the current is bigger than the voltage when the gate source voltage equal -2.5. The current here, it's less than 2, and it's less than the current at VGS equal -5 or 0.5. Here we can say we have the same curve if we do compression with the VGS equal positively and the gate source voltage was equal 0, but with maximum current, it was like that. And the same thing, the ohmic law was act the behavior of the current, but with a bigger amount of current. Here, when the VGS equals 0, -1, -2, -3, -4, and yes, the last one was -4, and the punch of voltage was equal -4. That means the channel will at punch off voltage. That means the channel will be like switch off. Here, the maximum current when VGS equals 0, the minimum current, when the VGS equal punch off voltage. Let's focus on this point, it's very important. Maximum current, drain source current at VGS equals 0, minimum VDS current when VGS equal the punch off or the current here equals 0. Here, when VGS equals 0, the maximum current was equal 8 milliampere, minus 1 equal 4 milliampere, minus 2 equal 2 milliampere, minus 3 nearly from 0, minus 4 equal punch of voltage, the current equal 0. Here, the voltage from gate to source is controlling voltage of the junction field effect, curves of drain source versus and source drain voltage for various levels of gate source voltage can be developed for the junction field effect transistor. Here, the effect of the applied negatively biased gate source voltage is to establish the depletion region similar to this obtained with VGS gate source voltage equals 0. But let's focus on this but. But what's the difference here? With less amounts, but at lower levels of drain source voltage. Therefore, the result of applying negative bias to the gate is to reach saturation level at a lower level of VDS, drain source voltage, to reach lower saturation level. The resulting saturation level for drain current has been reduced and in fact will continue to decrease. A gate source voltage is made more and more negatively. Eventually, when gate source voltage equal minus punch of voltage, and in this example it was equal minus 4 volt, will be sufficiently minus negatively to establish a saturation level that is essentially at here equal 0 milliampere. And for all practical purposes, the devices has been turned off, switch off. The effect of varying the gate source gate voltage equal here connected at reverse bias and equal negatively voltage. The depletion region will grow. Let's focus here. We have some different. The effect of varying gate source voltage, and we will apply more negatively voltage, the depletion region will grow more from these both sides, will grow at the same amount at same levels. The reverse bias gate junction produced a depletion layer in the region of the channel. The gate voltage controls the thickness, controlled on two things: thickness of the depletion layer and hence the thickness of the channel. The thickness of the depletion layer and the thickness of the channel. Consider an N-channel device. The gate will always be negatively with respect to the source to keep the junction between the gate and the channel reverse bias. Making the gate more negatively, what will happen if we making the gate more negatively? Actually, we will see a huge difference between some levels, some situations when it increase more negatively, what will be at the gate region. Let's know what will happen in increasing the resistance of the channel. When increasing the thickness of the depletion, the resistance will increase. And at the same time, we will not reducing in the width of the channel. That's mean increasing the thickness of the depletion will increase the resistance and will decrease the channel at the same time. Here, two polarities. Here we will talk about we done from junction field effect transistor. We know what his advantage. We know why he has 3 legs and what the similarity between it and between the bipolar junction transistor. We know how and when we use it. We done from understanding the curves IV curves when gate source equals 0 or equal more negatively, and when VGS equals 0 or more positively. And we studied all the important information about when it is at 0 biased. Now let's take the second kind of junction field effect transistor. It's material oxide semiconductor field effect transistor. It has two polarities, N channel, P channel, but here we will see some difference about the outer shape. Here we have more terminal, a substrate, and it's actually will connect directly with the source to be has 3 terminals like the previous junction field effect transistor. And here, like we say, drain, gate, source are the same, but the minority, it's different. Here, the minority will be near from substrate, will be at the right side, not at the left side. At N side, at P side, and at P channel, the N will be near from substrate, will be at the right side. And we will say, we can say we're dealing here with P side, with P kind of MOSFET field effect transistor, because here I'm seeing the majority are these two sides at up and down points. Because that I can select, here I'm dealing with P type of MOSFET. Here, let me catch that. Gate volt controls the thickness. Gate volts will control on the thickness, will select, will choose, will determine the thickness of the channel. And let's know how. Has two kinds, like I said. Consider an N-channel device, two polarities, N-type, P-type, and two kinds, enhanced and depleted. Let's know what all of these. Here, this image illustrates to us the enhanced kind of MOSFET, and here depleted kind of MOSFET. The huge difference between them, just in my opinion, just two important different things between the enhanced and depleted. At first, we connected it by using forward biased, positively terminal. What that's mean? That's mean the gate charge will be positively. What that's mean? That's mean the positively charged will attract the electrons to be near from it to make the gate region be bigger than, because that this region it's bigger than, and here it's smaller than. Here connected by using reverse bias, the gate channel is negatively, the gate region is smaller. Let's take a look to all of that, to all of these circles. Here, the gate region is smaller, and here connected by using reverse bias. Gates as described above are termed depletion, enhanced MOSFETs, or depleted MOSFETs. Some MOSFETs are constructed so that in the absence, if we don't have any gate voltage, there is no channel. It's important. If we don't have gate voltage, that means we don't have any channel. Such devices can be operated in enhancement mode, but not in a depletion mode. Since there is no channel to deplete, both forms of MOSFET are available as either N channel and P channel. Let's take a look at that. The depleted MOSFET has N channel like that. The arrow go in. The depleted MOSFET at P type of P type, the arrow go out. and here enhancement will be the same thing, but with interrupts of some interrupts inside this circle. At N type, the arrow go in, P type, the arrow go out. Here, we connected all of that to take a look to enhancement and depleted at the same time. What is the difference between MOSFET and junction field effect transistor? After we finished, we done from the MOSFET field effect transistor, and at previous slides, we understood what does that mean, the junction field effect transistor. Let's do some comparison between all of them and know what the difference between them. MOSFET have higher input resistance, small leakage current. That's mean low, higher, or we can say low input resistance at the same time low leakage current. Have great characteristic like less flat. That will be very helpful to us to introduce some electric things, including a less resistance. And MOSFET devices are more useful in electrometer applications. MOSFET can handle more power compared to that's mean higher input impedance, smaller leakage, have less flat, indicating a less resistance, and can handle more power compared with bipolar junction transistor. Here to junction field effect transistor, the majority will be at the left side. At MOSFET, the minority will be at the right side. Now the gate is the control input. In each case, the drain current is controlled by the voltage applied to the gate. That means the gate voltage is very important. Like I said before, if we don't have voltage applied, that means we in zero bias with respect to the source. These some pictures to bipolar junction transistor has 3 legs with different shapes, but at the last has a huge similarity, or we can say it's the same, with the field effect transistor. All of these has 3 legs, and all of these with Schottky diode has 3 legs. And here, like we said, here gate, drain, source, or we can say gate, drain, source. And here emitter, Schottky bias, and the last was the silicon terminal. It was negatively, and here A and the bias, the last one is the collector. Here the emitter bias the collector. That's right, some huge similarity with the shape, but with a huge difference with the applications, with the uses, with the many using each one. We use it in different field, because that's right, we have some huge similarity at the shape, but with different uses. Thanks, have a good day, and thank you about your listening, your patience. Let me stop.